Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with lecture 57 of our electrical machines subject. So today actually we will understand numerically how does this synchronizing power came to place, okay? Intuition wise we understood like what is synchronizing power, what does it mean. Today we will understand numerically and also we'll write down the definitions, okay? All the definitions will be there. Also of course in the previous lecture also we discussed about hunting. So synchronizing power and hunting both go hand in hand. So today we will discuss about more about hunting. How can I reduce hunting with the help of damper windings? Okay, so let's first start with this one, that for a cylindrical pole rotor this is the expression for power and this is the expression for reactive power, right? And this was the stable region and this was the unstable region. Why is it the stable, why is this is the unstable, already have been cleared in the previous lecture. So today I just want to focus on one thing. First thing is, when is my power maximum? Power is maximum at the edge of the stable and the unstable region, right? At this point the power is maximum. So what is the what is the delta here? Delta at maximum power is maximum when my delta is equals to 90 degrees. When my delta is equals to 90 degrees, then the power is maximum. So from here I can actually get a very important conclusion. What is the conclusion? Conclusion is that what is the delta equals to 90 here? So what do I observe? Delta equals to 90, cos 90 is 0. So it is minus Vt. So at P maximum my Q is minus Vt square by XS. Does it ring any bells to your head? It is negative. Negative reactive power means what? It is leading reactive power. Does it make sense? Intuitively, does it make sense? So here I have a generator, then I have a reactance XS, and that I am saying that the load is operating in leading reactive power. That means basically, if the generator has to supply maximum power, load must be leading. Why? Because load shall supply this reactive power, right, to the reactance. Load will supply the reactive power, not generator. Generator only will supply the active power P. Okay, so that's why reactive power is negative. Basically load is supplying the reactive power so that it compensates, right? Because we will see reactive power compensation, there we will see the power factor will improve only if load is leading. Okay, so that is a very important conclusion. This can be asked in a MCQ question. They can ask, when the power is maximum, what kind of load shall be connected? So it should be a leading load. For the power to become maximum, the load that shall be connected is leading load. So that's a very important conclusion. Okay, load should be leading power factor load. Okay, so this point is clear. Now let us numerically understand why uh, why this is called as the synchronizing power. Okay, numerically we want to understand why it might be called as the uh, synchronizing power. Okay, so let me do one thing. That let's assume that initially I was operating here delta naught, then I change to this point, right? This point is basically del delta. Okay, very small del delta. So what will be the change in power? So here, right, sudden change, sudden change. Okay, so can I derive P value? So what is my PE? PE is E VT EF VT sine delta divided by XS. Now from delta I am changing it to del naught plus delta, right? So my P, like my power P dash is changing to EF VT because initially it was delta naught, now it has changed to delta naught plus delta. Correct? So my initial power was this EF VT plus into sine delta naught divided by XS. Now my power will be EFVT by XS into sine delta naught has changed to delta naught plus del delta due to small disturbance. Remember, del delta is very small, very small, very small. Okay, so I can break this down into a formula. Sin A, it is sin A plus B, right? So it will be sin A cos B, P dash will be equals to, this will be constant EFVT by XS into sin A cos B plus sin B cos A. Okay, now very important point, remember your del delta is very small. If del delta is very small, then cos of del delta will be roughly equals to 1. Cos of del delta will be roughly equals to 1. Also, if your del delta is very small, right, I can directly say that sine of del delta, as del delta is very small, almost be equals to del delta only. Okay, this approximation we can do. So from here, what I can notice that it is P dash. If I break it down, so this will be 1. This is what EFVT sine delta naught by XS. It is same as this one, right? So it is basically equals to P naught plus, this is only del delta, right? Del delta, and this will be cos delta naught. So here plus EFVT by XS del delta. I will write the del delta outside into cos of delta naught into delta. Okay, so what I can say is, if I bring this on the left hand side, what is it? So it is basically like this is what is my PE dash minus PE naught. It is something like minus final minus initial, correct? Final minus initial, right? So final minus initial will be just what? Delta P, change in power, change in requirement of power. Initially this was a developed power, now the change in develop now the required power is this much, right? So final minus initial, so this will be final minus initial delta P, change in power will be equals to this value, right? This value I will copy into delta del. So this much amount of power change there needs to be produced. Who will produce this? Who will like deliver this much, like this much? Basically when there is certain disturbance from here to here, if I change the rotor angle suddenly, this much amount of extra power needs to be generated, right? For a motor, let's say I'm like giving a load for a motor I'm discussing, same will be happening for a generator as well. Okay, so for a motor, if I am suddenly changing the torque angle here, someone needs to supply that extra power. So this is the amount of extra power that needs to be supplied according to the change in delta. So this power is actually called as the synchronizing power, PSI. Is this term familiar to you? Sorry, this whole power is known as the synchronizing power. This whole power is known as the synchronizing power, and this term is actually known as the synchronizing power. Synchronizing power coefficient. This term is known as the synchronizing power coefficient. That's it. Okay, so yeah, I hope you are able to understand the thing. This is coefficient. This is the amount of power that needs to be generated with respect to this change in delta. Okay, so what is this? So it is basically delta P upon delta delta del delta is this value, right? Okay, this is not right. Okay, so from here I hope now it is clear. It is what, this is same as this one, right? If I differentiate this with respect to delta, I will get back this now. Okay, so that's why this is called as a synchronizing coefficient, because it helps us bring the motor back to stable point, into this delta stable point, because this much amount of additional power is required. Who will provide that? Synchronizing power. Okay, so if the synchronizing power is very high, right, what will happen? Even if there is large change, I will be able to provide that amount of power. If the synchronizing power coefficient is very large, I will be able to provide that extra power. If it is small, near here, right, so even if there is very slight change, I will not be able to provide the synchronizing power, because it is negative over here. Okay, it is negative, so it will move to unstable. So that's why, even though this is the point of maximum power, but we will never operate here. We will always operate in this region. Okay, I mean on the left hand side basically, because it is very close to unstable. So what we'll do, we will always try to increase our Pmax. If I increase my Pmax, that is EFVT by XS, right, then this point will go more up, so I will have more room to provide more power. So our main target will be to increase the Pmax value. Okay, in power system we will discuss about increasing the Pmax. Okay, same graph we will plot in power system, you will remember. So now I hope numerically it is clear what does synchronizing power coefficient means to you. Okay, I hope I'm able to clear it out. I hope I'm able to clear the reactive power, okay, all those things. So this is the synchronizing power, that is the extra power required to bring the machine back in synchronism. Okay, this much amount of power is required, because due to sudden transient load. Okay, so this is the synchronizing power coefficient, right? Synchronizing power basically coefficient. Sorry, this is the synchronizing power coefficient, and sorry, this is the amount of synchronizing power. This much amount of synchronizing power I will require, and this is the amount synchronizing power coefficient. Okay. Okay, I hope that is clear to you. Yes. Okay. So yeah, I hope now everything is clear. Now we will start to derive the torque expression. What is the expression for synchronizing power torque? Before that, I want to discuss about salient pole. Okay, in salient pole, the expression for power is something different. So we have this excitation power is there, but we also have this reluctance power. So I think I forgot to draw the graph previously, right, of the power of the salient pole. So we have this 2 delta term, right, that is in addition. So this one is the first term, that is this one, right? This we already know. So I have to plot this. It is 2 delta. That means here the time period is half actually. So in one cycle of the green graph, I will cover 2 cycles, or in 1/2 period I will cover a whole period of the blue graph. So it will totally complete a cycle here, and this will be a green cycle. So if I superimpose the two graphs, okay, so this will be of lower magnitude because the reluctance power will be generally lower value than the excitation power. Okay, so if I add this, what I observe is when both of them are positive, of course the graph will be still in both of them here, right? Graph is increasing, this is also increasing. Okay, but here if you see suddenly graph is increasing here for the blue graph, and the green graph is also increasing here, right, till this point. This point is what? This point is pi by 4. Am I correct? This point should be pi by 4, because after pi by 4 this starts to reduce. This point will be pi by 4 here. So we want to find out the stability region. Again, the stability region will be the point where the graph, the resultant superimposed power graph, starts to reduce. It will be somewhat lower than pi by 2. Okay, I can derive it. I can derive it when the power is maximum, and at that value we can get the value of delta, to which we can derive the expression when the power will be maximum. Okay, and you can see the reactive power. Again, you will observe that the reactive power will be what? Reactive power will be uh, leading. Okay, you will put it in the formula, you will say. So what you will do, like I will this is the homework task for you. You will differentiate this power with respect to delta, right, and make it 0. Okay, also you will you will double differentiate the power with respect to delta, and make sure whatever points you get, that is less than 0. If that is less than 0, then you will get a maximum. Okay, so this is the task, and from here you will see that your PE max, right, will happen somewhat lower than pi by 2. Okay, it will happen more earlier. So now even lesser amount of delta bandwidth I have for stable region. So now the stable region will be somewhat lower. So stability has reduced. Although power, right, this maximum power is increased, but the stability has reduced. Okay, so stability region of stable operation has reduced. Okay, just give me 1 second. Yeah, so yeah, just give me 1 second now. Now yeah, I was just seeing something bit of controversy happening. So yeah, now let's like this is very important key point, right? This is very important. Pi by 2 delta, like 90 degree, both are same, right? I hope we are able to convert radians and degrees. This much you are able to do. Okay, so now let's come to the next point, that is uh, regarding the synchronizing power, I will derive the synchronizing torque just in a second. Okay, I will discuss about the, I will derive the expression for uh, synchronizing power. Okay, that also I will derive, don't worry. So we have this synchronizing power and torque. Synchronizing power generally is mentioned for generators, synchronizing torque is generally mentioned for motors. Okay, so synchronous machines, both motors generators and motors are designed to operate at a constant synchronous speed. Synchronous machines that are designed to operate at a constant speed. So synchronous machines are designed to operate at a constant speed. However, in real world scenarios, they can experience disturbances. Okay, if I suddenly give it a load, if the suddenly the load current has increased, right? It's for a generator, for a motor, a mechanical load has increased. Okay, then they will experience disturbances. These disturbances often are referred to as transient. Just like simply RC circuit, condition has changed suddenly, right? So that is known as the transient state. So also this synchronous machines also will feel a transient state, and can there can be sudden changes due to the sudden changes in mechanical load or supply voltage fluctuations, or due to some electrical load suddenly getting connected due to some short circuit, due to some fault. We will understand this in power system. There will be faults in the system, there will be sudden changes. So for according to that, we have to improve our this like improve our machine, synchronizing power, all those things, right? The synchronizing when such a disturbance occurs, the rotor of the machine momentarily deviates from its synchronous position. So previously both of them had its angle, rotor and stator had an angle delta, right? So they will deviate due to that sudden disturbance, they will suddenly deviate. I will draw this in a better manner. NR, NS. Okay, they will deviate. To maintain synchronism and bring the rotor back to its steady state operating point, the machine develops what is called synchronizing power and synchronizing torque. Okay, synchronizing power and torque are the same thing basically. So what is synchronizing torque? Synchronizing torque will be uh, this Psy upon omega s. That's it. Like I hope you will be able to do it, right? Synchronizing torque will be Psy upon omega s. That's it. Okay, and remember here, right, this delta naught, always write this delta naught in radians. Okay, here if you are putting delta naught, this should be in radians, though not in degrees. This delta naught will be in radians, not in degrees. Just be careful. Okay, so the synchronizing power is the extra power developed within a synchronous machine that acts to restore synchronism when rotor momentarily deviates from the its steady state position due to disturbance. It's the machine's inherent ability to resist being pulled out of synchronism. Okay, so when a sudden load change happens, then delta value momentarily changes. This change in load angle causes an immediate change in the electrical power developed. This extra power, the synchronizing power, helps to match the new load demand and pull the rotor back to synchronism. So new steady state delta value will change obviously, but it will help it bring it back to synchronism because the NR value, rotor speed, will reduce, right? Already discussed in the previous lecture. Okay, so the same explanation is given over here for a synchronous motor. If a sudden load increase causes the rotor momentarily to slow down, so if there is suddenly load increase, then the rotor will slow down, so NR will reduce, right? Then what will happen? Then the angle delta will increase, then power has to increase. Who will provide this extra increase in power? Synchronizing power coefficient. Okay, this increased delta will result in a higher electrical power absorption, which acts to accelerate the rotor and bring it back to synchronous speed. Conversely, if the load suddenly decreases, opposite will happen. Okay, for a synchronous generator, similarly, if a sudden electrical load is applied to a generator, suddenly if I apply electrical load, again there is a delta of power, right? Power has increased, so delta also has to increase. Delta has to increase, so it may bring the rotor momentarily slow down. Again, if the power has increased, that is Pm is greater than P, then what, your d omega s by dt will be negative. If your d omega s by dt is negative, then your omega s will reduce. If your omega s reduces, then that means what? That means your delta will increase. Same thing will happen. So again, to bring it back to synchronism, the active power has to increase. Who will provide that? Synchronizing power. Okay. So I hope that those things are clear. So these are the equations. This is the synchronizing power coefficient. Okay. This is the synchronizing power coefficient. Remember, this is the synchronizing power coefficient, not the synchronizing power. So it is dpsy upon delta. Okay. For a cylindrical rotor, the synchronizing power, this is the power, and synchronizing power coefficient is this. Okay. Coefficient, not the synchronizing power. Okay. So what is the unit of this? So remember, here the unit of this is watt per electrical radian. Okay, unit of this is electrical radian. If your delta is in degree, so first you have to convert your delta into radian. How will you convert your delta into radian? Let's say if your delta is in mechanical degree, so your first task would be to convert your delta into what? Into mechanical radians. So how do I convert into mechanical radians? It will be pi into delta by 180. That will convert into mechanical radians. Next, your delta must be basically in electrical radians, right? It should not be in mechanical radians, it should be in electrical radians. So how will I convert it into electrical radians? So how do I convert this into electrical radians? So what you will do, I know that one thing I know, right? What do I know? What do I remember? That my electrical angle is equals to p by 2 of theta mechanical. This much I remember. Am I correct? Electrical angle will be always higher than theta mechanical. How can you remember? Let's say I have a 4-pole machine, right? 4-pole machine. North, south. Poles will always be alternating north, south. So in a whole 360-degree rotation, how many electrical deviations are there? So from north to south there will be a whole of 180 degree, right? So if I'm mechanically rotating, let's say if I'm mechanically rotating 360, how many north south I have? 1 2 3 4, right? 1 2 3 4. So electrically from here to here there will be, like, basically if my conductor is here, initially the flux here will be maximum positive, then when my conductor will reach here, flux here will be maximum negative. So this is just a half cycle, right? Again when I will reach here, again the flux will become maximum positive. Again when I will reach here, again my flux will become maximum negative. So if I observe, this is a cycle, right? Again this is a cycle of the flux waveform. Again if I reach here, it will become maximum positive, right? North pole. So all this I've already explained in my DC machines, so I'm just going through this quickly for you to understand. So again I will reach here. Okay, so what do I notice? That this is what, this hole is a 360-degree mechanical. I'm just explaining you how to remember it, right? Mechanical and electrical. But in a 360-degree mechanical, electrically my flux waveform is changing twice, right? So electrically it is actually 720 degrees. So from here I can get the equation, right? Theta electrical by theta mechanical is 2. How many poles I have? 4. So basically it is 4 by 2. So from here I can remember the expression. I am just explaining you how to remember the expression, right? That if let's say I have a 4-pole machine, right? If I rotate, if I start from this point, my conductor is here, north pole. So flux lines will be maximum like this. It will go from north to south, right? So it is maximum inwards. So inwards I have assumed to be positive. Then again I see flux lines here will be maximum outwards. Outwards I have assumed to be maximum negative. Again maximum inwards here, again maximum outwards. So in one mechanical cycle, in one rotation, electrically it is completing 2 cycles. So that's how we get the result. Or you can take example of 2-pole machine. Both will work. 2-pole machine also will work very simply. Conductor is here and here. So in a whole rotation of 360, electrically actually it will cover twice, 2 cycles. Same thing. Okay. So let me do one thing. So this is one mechanical radian, right? This is one mechanical radian, correct? So if I replace theta m here, so one mechanical radian is this much. So this is my theta m basically, right? Mechanical. So my theta e will be what? Theta e will be p by 2 times pi delta divided by 180 degree, correct? This is in mechanical degree. I just converted this into mechanical radian. This is my theta m basically in radians. Okay. So this is my theta e actually. Theta is this much. So if I want to, so what is my delta e? Delta e will be this, sorry, not theta, sorry, delta e. So I will replace it. So if I want to convert from mechanical to electrical, I have to just multiply this constant term, because remember your delta here is in mechanical degree. Don't forget this. So basically this, right, I have to multiply an additional constant. So if I want to write my PSY, in, if my delta is in mechanical degree, dPe upon d delta, what delta is in mechanical degree, then we have to multiply this extra constant. So p by 360, p pi by 360. Okay, sorry. So this will get multiplied in the bottom, right? Because del delta. So this will get multiplied in the bottom. So this will be basically, let me write here delta m, otherwise you will get confused. So this is my dPe by delta e, right? So I can convert delta e into mechanical. So this will become in the bottom a constant term will be multiplied. So p pi, remember this is delta m, right? This is delta m. Okay, this is delta m. Delta m why am I concerned about mechanical? Because in torque, right, mechanical angle is provided. So that's why I'm concerned about mechanical. Okay, I hope that is clear to you. So this will be p pi (360) into delta PE by delta theta m, delta m, right? So this will be the conversion. So I hope it is clear that if I want to convert into here, remember your delta will be mechanical m. So what will be your, like, what will be your delta PE upon delta m? So I will take this on the right hand side. So if I know the synchronizing power and if I multiply this by p pi by 360, I will get my delta PE by delta m, right? So I will do that. So my delta PE, I am just doing conversion. I am just doing unit conversion. So my delta PE by delta m in mechanical, this is what, this is watts per mechanical degree. Just doing unit conversion, that's it, will be equals to this, will go on the left hand side, right? Synchronizing power p pi upon 360 into synchronizing power. Now what is what is synchronizing power? Synchronizing power we have already derived. Synchronizing power is this value, right? EF Vt by cos delta. So I will replace it. So EF into Vt by xs into cos delta. So this also can be asked. Okay, this also can be asked actually. What is the value of synchronizing power coefficient in mechanical degrees? Okay, synchronizing power coefficient in watts per mechanical degree. This is the synchronizing power. This is the synchronizing power. Okay, if you remember, this was the PSY, right? Sorry, this is the PSY. Yeah, PSY is this dP upon delta. So this is the synchronizing power. Sorry, this is the synchronizing power coefficient, right? So this I already have derived. So I will just replace the value. So from here I will be able to get my synchronizing power coefficient in what? In watt per mechanical radian. Okay, watt per mechanical radian. Now if I want to convert this into torque, so this is my PSY in watt per mechanical radian, sorry, watt per mechanical degree. If I want to write my torque, right, torque in, like, basically the synchronizing torque coefficient. So this will be synchronizing torque coefficient. This will be equals to, remember, your torque is with respect to the overall power. If it's a three phase system, the power will be 3 into PSY, right? Why? Because this is a per phase quantity. PSY here is a per phase quantity. Okay, so if it's a three phase quantity, I have to divide it by per phase. Okay, I hope that is clear. So synchronizing torque coefficient again will have 2 units. Okay, synchronizing torque coefficient again will have 2 units. So the normal one, T synchronizing, will be PSY upon omega s into M. Okay, what is M? M is the number of phases. M is the number of phases. What is PSY? PSY is PE upon del PE upon del delta E, if it is in electrical radian per second. Okay, and it will be equals to M by omega s into del PE by del delta M, if my delta M is in mechanical radians. Okay, so delta E is what? Delta E is electrical radians. Oh, sorry, I have to multiply this constant, right? This constant will be there to convert anything in from mechanical degree to electrical radians. This term needs to be multiplied. So this will be P by pi into 360. This will be always there. Okay, so your delta E is the standard format, that is electrical radian, and your delta M is in mechanical degrees. Mechanical okay. Okay, so yeah, I hope that is clear now. So same thing is written over here. Okay, PSY upon omega s into M, and PSY is in either is an electrical, like PSY unit will be electrical, sorry, watt per electrical radian, or you can convert it into watt per mechanical degrees. Okay, M is the number of phases, because this is a single phase power, right? And M is the number of phases. This also can be asked. Now let me derive one more thing, the expression of synchronizing current, because how much transient current will it take, right? So that is what I want to derive. So now let's discuss the amount of synchronizing current that it will take. Okay, that is what I want to derive right now. So let's discuss about the synchronizing current. Why? Because if there is change in delta, right, there is change in, like, there is change in power, then there will be change in delta. If there is change in delta, there will be change in current, delta I. I want to calculate how much change there is in I. Okay, because remember, what are fixed? Your excitation is fixed, your Vt is fixed, everything is fixed, right? Your synchronous reactance is fixed, and your frequency, all these are constant. Okay, all these are constant. And if I have, let's take for the case of motor, let's take for the case of motor. If I take the case of motor, so I will have this EF angle delta here, like this will be lagging, remember this is VT angle 0 and this is JXS, right, XS. Current will flow like this. Okay, so this is a, these are constant. Suddenly there is load change, due to that there will be delta change, right, delta change. So let's draw the phasor over here. So let's assume that my VT is here. Okay, this is my VT. And this is my EF, right? EF will lag somewhat. And let's assume that initially they were operating at some angle delta naught. Initially they were operating at some angle delta naught. And initially the what was the current due to that angle? Let's assume that current was also lagging. This was the current. Okay, let's assume that this is IA, this was theta, and this is psi. So like what is the equation, basic phasor equation? I know my VT will be equals to EF minus, sorry, EF plus J XS into IA. Okay, so J XS into IA plus J XS, so plus J will be somewhere here and it will totally touch the voltage, right? So this length is J into IA XS. Okay, so now what will happen if there is a sudden change in EF? Because this is constant, right? This thing is constant, EF magnitude is constant, but there is sudden change in delta, sorry, in delta. So from delta naught it switches to, let's say, del delta, right? From delta naught it has changed its position. So of course its magnitude is constant, so it will revolve around this circle only, it will not change, it will revolve around the circle only. So let me do one thing, let me draw this in a different phasor, otherwise you will get confused. So this was the initial case, okay, initial case, initial, but delta equals to delta naught, and this is the transient state where suddenly my delta changed to delta naught plus del delta. So this angle will be how much? This angle will be like what I will do, I will increase angle to, I will increase it so that you are able to understand it better, because I want it to make more obvious. So let me delete this angle. Okay, so this will be what? This will be actually delta naught. So what will happen here? Your IA value will increase. IA magnitude of IA will increase, right? If you see, because previously this much amount of IA current was required, but now this much amount of IA current is required. So it is greater. So IA current is even greater. So how much is the additional current? Who will provide that? Synchronizing current. So this current, right? So basically what will happen is now a new line will be drawn. That will be this line. Okay. So now IA has changed to IA dash. This is the IA dash, and this much is the additional current, that is the synchronizing current. I hope it is clear. This much is the additional current, that is the synchronizing current. How will I find out this current? Okay, just one neat trick we will do to find it out. So how much is this drop actually? This much drop is ISY into what? XS, correct? One more thing is this length is EF, this length is also EF, and this is a straight like line. So this angle and this angle also will be same. Okay, so it is a isosceles triangle. So if I draw this triangle here perfectly, okay, the triangle, if I draw it in a better manner, So this will be the triangle, okay, and this is the line, okay. So this length is EF, this length is EF, this length is EF, this length is the additional current, that is ISY into XS, okay. This is delta, this is not delta, delta, right. This much is theta, this is also theta, both lengths are same. So it is a isoscale scale triangle, it is a isoscale triangle, right. It is a, this is a what, isoscale triangle. So iso, one property we have, we don't even need to remember the property, I will still solve it using basics, okay. Isoscale triangle, I'll use the basics. So basics will be that if I draw the perpendicular bisector here, right, okay, although it does not look a perpendicular bisector, so this, how much length will be this, the half length, it will be just the half length, right, this length will be just half. Half length, right. And what will be this angle, it is a perpendicular bisector, right, so this will be delta by 2. So one property I can use, what is that property, I can use the property of this one, right. If you remember that if I have a triangle here, any random triangle, right, if let's say this is angle A, angle A, angle B, angle C, and this length is, let's say, LC. So I can write that my length LC divided by sine of the angle sine C will be equals to length, this length will be opposite LB, LA. This is a very basic property of triangle. I hope you remember. Even if you don't remember, still you can solve with Pythagoras. You can solve with Pythagoras, okay? But this is a very basic property of triangle, right? LB upon sine B will be equals to, like, you can write it other way around as well. It will be same, LA upon sine A, okay? So what I can write over here, that my this over this, right, ISY upon ISY by 2, ISY into XS divided by 2 divided by the sine of this angle, sine of delta by 2 is equals to this EF divided by sine of 90. What is sine 90? It is 1. So EF divided by sine 90. So from here I can get the very basic value of ISY. This is a very important relation that can be asked in examinations, okay. So even if you forget, right, just remember how are you able to derive it. Remember how are you able to derive it. So this will be ISY into JXS, okay. ISY will be equals to 2 EF sine delta by 2. So this will be the expression for ISY. Now what will be the phase? Can you tell me what will be the phase of ISY, synchronizing coefficient current? So if you observe, right, this phase will be, it has shifted by delta by 2, right. This is JISY, this is JISY. So if this EF has shifted by delta delta by 2, right, what will be the, so I want to calculate what will be the phase. So this is what, this is actually J into ISY XS, okay. So if you observe here, this is the drop, right, this is drop, this is what, J into ISY XX. So what will be ISY? ISY will be perpendicular to this line. What is perpendicular? This line, right, this line is perpendicular, this line is perpendicular. So this will be the direction of my ISY, this will be the direction of ISY, correct. So like basic thing is, my ISY will be perpendicular to J into ISY into XS. Very simple. So J into ISY is in this direction, right? Is in this direction. So ISY will be here in this direction. So what is the angle of ISY with respect to the initial reference? Remember, your EF is here. Your EF is here, right? So this is delta by 2. This angle is delta by 2. So with respect to EF, it is minus delta by 2 because it is lagging. The angle of ISY with respect to EF is minus delta by 2. But remember, your EF is already lagging with delta naught. Okay. So from VT. So with respect to the reference, what will be the angle? So with respect to the I'll explain. So ISY angle with respect to EF is minus delta by 2 because this much angle is delta by 2 and it is lagging. So it will be minus delta by 2. So angle of ISY with respect to EF will be minus delta by 2. Okay. And my what will be the angle with respect to reference? Angle of ESY with respect to reference, that is VT, right, will be, remember this much angle is minus delta naught, right? Because delta naught is positive, some positive values, that's why I have to add a negative sign. So this is minus, this much angle is delta naught, okay, this much angle is delta naught and this much is delta naught by 2. So actually here, right, if delta naught is assumed to be a positive number, then I can say it is minus of delta naught minus delta by 2 if I assume my delta naught to be a positive number. So this negative sign just represents that it is lagging. Okay, so actually the overall current, okay, here, right, otherwise you will get confused. If I say delta, okay, this delta, right, if it's not negative, then you will get confused. What shall I do? I know you will get confused because if I assume that delta naught is positive, you will get confused. But still, yeah, if I assume delta naught is negative, you will get confused. So let's assume that your delta is greater than 0, so that I have to add a minus and why? Because power flow should always happen from higher angle to lower angle. So this should be at higher angle, this should be at lower angle. Already has been discussed in the previous to previous lecture, right? So ISY will be, sorry, if your delta naught is greater than 0, that is positive number, then only I will add a negative sign over here. So ISY actual value will be 2EF sine delta by 2 into angle minus of delta naught plus delta by 2. Okay, this will be the complete expression for ISY. Although not that important, but like this negative sign basically represents that it is lagging. Lag. Okay, it is lagging. That's it. So I hope all these confusions are clear now. So yeah, this is the expression for torque. We have already discussed. Stability. The stability of synchronous machine is intrinsically linked to its load angle. Stable operation when my rotor angle for cylindrical rotors will be between 0 to 90. Maximum power point will be 90. Okay. Unstable region, if delta is greater than 90, then it will be unstable. For salient pole, it will be somewhat lower than 90 because it goes negative. Okay. So what is stiffness? In context of synchronous machine, stiffness refers to the synchronizing power coefficient. Stiffness is same as synchronizing power coefficient. If they are mentioning about stiffness, they are mentioning about synchronizing power coefficient. A higher or more positive synchronizing power coefficient means that given for a change in delta, the machine develops a larger restoring torque that will make it more resistance to losing synchronism. Okay, if the synchronizing torque or the stiffness of the machine is higher, then I have more power that it can generate to bring the machine back into synchronism. Okay, so synchronizing power coefficient already has been discussed. That is what we mean by stiffness. Stiffness is same as the synchronizing power coefficient. Okay, now let's discuss what will happen at different excitation. Okay, if I overexcite the machine, if I underexcite the machine, what will happen? If I overexcite the machine, that means my IF is increasing. If IF is increasing, that means my EF is increasing. If EF is increasing, the basically what will happen? The active power for the, if all other values are same, P is equals to what? EF Vt by XS sin delta. If all the other values are constant, if I increase EF for the same value of power angle, I am getting more power. Okay, for the same value of power angle, I am getting more power. So for a given active power output, the load angle, so what will happen, or if I want to say in other words, if I say that my power is constant, if I say my power is constant, right? If my power is constant and I say that I am changing EF, VTXS is anyways constant. So basically my EF into EF into sine delta has to be constant. This I think we have discussed previously as well. So if I am increasing excitation, then sine delta has to reduce to keep the power constant, right? For the same power, if I am increasing excitation, sine delta has to reduce. That basically means that my system will be more stable. So for an overexcited synchronous machine, the system will be more stable. Okay, so yeah, same thing is written over here, that of an overexcited machine, the for a given active power, the load angle of an overexcited machine is smaller compared to a underexcited. We will see for underexcited it will just be the opposite. For a underexcited machine, it will just be the opposite. This is because increased EF allows motor to maintain the same power with a smaller angle. So since delta is small, typically close to 0, cos delta will be high, so we get a larger synchronizing power. So a larger positive synchronizing coefficient means the overexcited machine has greater synchronizing torque and is thus stiffer. It can tolerate larger load disturbances. So a overexcited synchronous machine can tolerate larger disturbances than a underexcited synchronous machine. That is the conclusion. In underexcited, what will happen? You will reduce the IF. I am underexciting it. That means EF will be reduced. If EF is reduced, that means what? That means your, again, power is constant. So your EF sin delta has to be constant. If your EF sin delta has to be constant, that means EF is reducing, sin delta has to increase. That means your delta has to increase. Power angle. If power angle is increasing, I'm going more towards instability. Okay. For the same active power, the load angle of an underexcited motor is generally larger compared to overexcited. The motor needs larger angle to develop torque due to reduced EF. So I need a larger angle. So here what will happen? The synchronizing power coefficient will be smaller. So the machine will be less stiffer. So a smaller positive synchronizing power coefficient means the underexcited motor has a reduced synchronizing torque and thus less stiff. It is more susceptible to losing synchronism with smaller load disturbances, making it less stable. So a overexcited synchronous machine, overexcited synchronous machine will be more stable than underexcited synchronous machine. Okay, inherently this is the property that it will follow. So overexcited motors are better at handling sudden significant load changes due to high stiffness. They can recover from transient. So this can be a interview question. Okay, I am covering everything. Interview question, like this can be asked in GATE as well as a MSQ. Okay, theoretical MSQ. So overexcited synchronous motors are widely used for power factor correction as well. We will see this in power system. Okay, don't worry, we will see this in power system. Okay, so this dual benefit further highlights their importance. So overexcited synchronous machine can be used in many cases. It will also, if the stiffness is increased, hunting also will be reduced. So we will see what is hunting just after solving few questions. Okay, so yeah, that is what we have discussed here. Power system stability will be improved. So let's solve two questions and from there we will try to understand about synchronizing power. Okay, so this is one of the question and this is the next question. Pause the video and try these two questions by yourself and then we will come back with the solutions. So let's solve this question. A synchronous generator is operating in an overexcited condition. Okay, it is operating in an overexcited condition. That means it is more stable. Delta will be lower. EF value is given to me as 1.5 pu, and XS is given to me as 1 pu, right? XS is 1 pu, and it is delivering a synchronous power P is equals to 1 pu of the bus. If the input from the prime mover is increased to 0.5%, so the input to the prime mover has been increased by 0.5%, that means your delta P will be, like, change in the prime mover will be 0.5%, 0.5% of initial power, right? That is a change. I have increased by 0.5. Okay, determine the resulting change in the active and reactive power delivered to the generator by the generator. So if I am increasing the input of the prime mover by 0.5%, then of course their RA is 0. RA is 0, that means the change in the output of the generator, delta P out, will be same, that is 0.5% of initial P. So what was initial P? 1 pu. So change in the output will be 0.5%, that is 0.5 divided by 100 into 1. Okay, so this will be 0.005 pu. So this will be the change in the output power, that is already fixed. But what is the change in reactive power? How do I find out the change in reactive power? So there are two ways to solve. First one is the basic method, method 1, basics. Okay, how will I solve using basic method? So it is, nothing is mentioned, right? Only XS is mentioned. That means it is a, if synchronous reactance is mentioned, it is a cylindrical rotor. So if I will just find out the initial Q, right, and I will find out the final Q, initial and final, and delta Q will be just final minus initial. Okay, I will just do this. So what was the formula for reactive power? So this, if you remember, it's very good. So one thing I remember, right, there was a voltage difference. There was this Vt square by Xs was there, right? Vt by Xs will be there. In common, there was a voltage difference. Now it was not exact voltage difference. It was like already sine delta, like the active power formula is what? Active power formula is EF Vt by Xs. I am just explaining how can you remember the formula for reactive power. So already sine delta has been used here. So I cannot use sine delta. With EF, some cos or sine function came, right? Sine delta has been used here. So I will use here cos delta. Okay, minus, of course, Vt was there because there was a term Vt square by Xs, right? So it will be minus Vt. Okay, so this was the, this was the formula for reactive power, right? So for that I will actually need to find out the delta. How will I find out the delta? I will find out delta from here. So initial P naught will be equals to EF Vt, or initial Pi was equals to EF Vt divided by Xs sine of delta I, initial load angle, right? So EF I know, EF is 1.4, sorry 1.5, P I know, Xs I know, so sine delta will be what? Sine delta Sin delta I will be 2 by 3 basically. It is 1 by 1.3, 2 by 3. So 2 by 3, if I just calculate what is delta I, so 2 divided by 3 sine inverse, so it comes out to be 41.81 degree. Okay, so delta I will come out to be 41.81 degree. Okay, so this is my delta I, initial delta I, right? So I will be able to find out my QI. So what will be my QI? So initial reactive power will be Vt is 1, Xs is 1, Ef is 1.5, cos of 41, cos of this, right, 41.85 is 0.7453 minus 1. This will be equals to into 1.5 minus 1. Okay, so 0.1118. Okay, pu. This was the initial reactive power. Now I have to find out the final reactive power, right? Final. So how will I find out the final reactive power? By changing, like, if the power has changed, right, the new power, right, pf, what is the new power? Pf is 1 point, although the increase is very small, but still there is some considerable amount of increase. Okay, so pf is 1.11. So from here I will be able to find out my delta f, right? So what will be delta f? So again this will be equals to ef into Vt by Xs into sine delta f. There will be some change in the angle. Okay, there will be some change in the angle. So from here I can easily find out what is the delta f. 0.005 divided by 1.5. Okay, okay, this also does not pick up the angle. Okay, it's 42.067. Okay, okay, yeah, it's changed. Okay, that's fine. This has changed, right? Yeah. So from here delta f comes out to be very small change, but there is some certain change, right? 42.067 degrees. What was the 1.5? Yeah, sorry, not this. Yeah, it is changed. It has changed. Delta has changed, right? So delta dash has changed now. So now what will be the final reactive power? So the final reactive power will be again using the same formula, Vt by Xs Ef into cos of this delta final, right? 42.067 cos of this is 0. This will change slightly, 0.742. I have to write down more numbers, right? 36. Okay, just to be accurate, minus 1. So into 1.5 and subtracted by 1. So now the new reactive power is 0.11354. Okay, so the delta f, so delta q is equals to q final minus q initial. So q final is 0.113. So of course the reactive power has reduced. Does it make sense? So we will try to see does it make sense or not. Okay, so this will be 0. 0.118. Previously we calculated, right? 0.118. So subtracted by 0.118, this will be minus of 0.00457. So this is the change in delta q. Okay, change in reactive power. Now can I do it with some other method? Method 2. because I know what is a change in power. I know what is a change in power. If I somehow am able to find out this relation, basically, if I am able to find out delta Q, because I have to find out change in delta Q with respect to change in power, right? If there is sudden change in the active power, then how much change there will be in the reactive power. That is my purpose. So if I'm able to find out this relation, right, some constant x, right, okay, so what will be x? X will be equals to delta Q upon delta P, or I can write delta change in change in reactive power with respect to change in active power. How will I find it out? There is a easier way to find this out. This will be equals to delta Q upon delta del into delta del upon delta P, right? So if I'm able to find out these two, right, then automatically they will get cancelled. So ultimately my value will be delta P upon delta Q only. Okay, so my x is this value, this is my x. So I will differentiate my P with respect to delta, and I will differentiate my Q with respect to delta. So what is delta Q upon delta, right? So it is delta Q upon delta. If I differentiate this, right, term here, it will be Vtx is constant. This will be EF sine delta. That's it. Vt EF by xs sine delta. Okay. And d P by d delta will be equals to what? EF Vt by cos delta, right? Okay, one more thing, differentiation of cos is what? Minus sign. Sorry, differentiation of cos will be minus sign. This will be minus, and dp upon d delta, it's just the synchronizing coefficient, that is EF Vt cos delta. EF Vt by xs cos delta. EF Vt by xs cos delta. Okay, so if I basically what is my x? X is this divided by this. So it will EF Vt by xs will get cancelled. Ultimately, basically my, if I want to find out delta Q, it will be equals to minus of tan delta into delta P. Okay, now let's solve it basically. So for this, right, I have to find out initial delta value. So what was the initial delta value what we computed? It was 41 point something, right? 41 point where is it? 41.81. Okay, this relation is only valid for a very small change in delta. Okay, so otherwise it will not be valid. So I will put here. So what will be my delta Q? Delta Q will be minus of tan of 41.81. So that is minus of 0.8944729 into delta P. What is the delta P? Delta P, if you remember, it was 0.005, right? This was the delta P. So this will be my delta Q. So multiplied by 0.005. So it comes out to be minus of 0.00447.2. So this is the change in delta Q, which is exactly what we solved here. So miraculously, we are actually correct. But please keep in mind that if in the question, this is the answer, okay, this is the answer. But if in the question they would have asked you the percentage change, so percentage change in delta q will be what? It will be delta q upon the base value, initial value, right? So delta q, change in delta q, that is minus 0.004457 upon the base, that is the initial value. Initial value is this much. Sorry, this is the final. Initial value is this much, 0.118. 0.118, okay, into 100 percentage, into 100 percentage, right, into 100. So here it comes out this divided by 0.118 into 100, it comes out to be minus 3.79%, okay. But here, right, it will not be same. Like few students, they get confused, they do what, they actually write this relation as percentage change in delta q will be equals to minus of tan delta into percentage change in delta p. This is absolutely wrong. Why? Can you tell me why it is wrong? Because remember, when you are talking about percentage change, that means what I am doing, I am dividing both sides, right? This relation, right? I will if I want to find out percentage change, what is the percentage change of delta q? It is delta q upon q initial. What is the percentage change of delta p? It is delta p upon p initial. So if I want to write this percentage change, here I am dividing by pi, but here I am dividing by qi. So I cannot divide both sides by different numbers and then say they are equal. That is not possible, right? So basically, if I say I have a equation here, that is 2 equals to 2, and then you say that you are dividing the left hand side by 3 and you are dividing by the right hand side by 5, will this relation be still valid? No, right? So this relation is not valid. So percentage wise they are not equal, okay. If it is not in percentage, directly the change in delta q, that I can directly relate here, okay. So please keep this in mind, percentage wise they will not be equal. If you want to write percentage, first you find out delta q, then you find out q initial, and then you write your percentage change in delta q, that will be equals to delta q upon q initial into 100, okay, then it will be valid. Just be careful regarding this question. So this question actually is pretty good, okay. Let's so this was the method 2. Basically method 2 was using a relation. So this relation is also very important. Either if you want to remember, you can remember it. This relation is also very good. So how to easily remember it? Easily you can remember that I know that my P is equals to Vi cos theta and Q is equals to Vi sin theta, right? So this I know, okay, this I know. So if I differentiate dq by d theta, okay, not that, let me not differentiate dq by d theta. So what will I do? I will divide q by p. Q by p will be what? It will be simply tan theta, right? From here I can easily say that it will be tan theta, and of course there will be some like negative change, because if I'm increasing the active power, then reactive power has to reduce. So that's why there is a negative change. So I'm just telling you how can you intuitively remember it, okay. This is how you can intuitively remember the formula. Let's now move on to the next question, okay. So a 400 volt 3-phase star connected salient pole synchronous machine. So it is a 400 volt, so Vt is equals to 400 volt. It is a star connected salient pole synchronous machine, that is my xd is equals to 6 ohms, okay, xd equals to 6 ohms, and I can say my xq, quadrature axis reactance, is equals to 4 ohms. The motor is operating with zero field excitation, that is it is unexcited. If it is operating with zero field excitation, will the power be zero? No, right? Power will still be zero. Power will still not be zero. Why? Because I have reluctance power. Okay, remember the formula for reluctance power. So in what condition can the maximum active power be transferred from the motor to the bus? What is the condition in which I can transfer the maximum power? So if you remember the formula for active power of a salient pole machine, like this was constant Vt EF by xd sin delta plus Vt sine 2 delta was there, Vt by 2, and here I had 1 by, if you remember, like which one will come first? Will the xq come first or xd? I remember this thing that xd is higher than xq, right? So xq will come first here and then xd, so that this term is positive. Okay, that's how you can remember it. That's how you can remember the thing. Okay, so uh, xq will come first, then xd will come. Okay, so divide by xd. This was the formula for into sine 2 delta, right? But they are telling me that ef is 0. So if ef is 0, basically my power then becomes Vt by 2. I will just quickly check whether I am writing the power formula correct or not. Otherwise, you guys will scream right at me. You guys will scream, and I don't want you guys to scream at me. Okay, where is it? Where is it? Yeah, it is. Okay, sorry. Here Vt square will be there. That's okay. I also tend to forget. Vt square should be there, right? Sorry, this Vt square should be there. Okay, so like this is also voltage into voltage. So here also voltage into voltage should be there. Okay, that I was thinking that I'm missing something. Okay, I was expecting I'm missing something. So this will be Vt square divided by 2 into 1 by xq minus 1 by xd. Now everything else is constant. What will be the condition for which power transfer will be maximum? That is delta equals to 45 degrees. If delta is 45 degrees, then power transfer will be maximum. So this was the answer of the first one. Answer of the first one. Then at this condition, maximum power transfer, determine the armature current. So we have to determine the armature current. What will be the armature current? Okay. So EF they have given me. EF they have not given me. Okay. So what is it? It is a motor, right? Motor, we know we have this reactance here, and then we have a this motor connected, and then we have bus Vt angle 0, right? So basically if I want to write the equation, EF angle delta, delta is negative, remember, Vt angle 0 minus resistance is not there, so J into IDXD and minus J into IQ XQ. Okay, so from here I can easily find out the armature. Okay, armature current I have to find out it. Armature current is what? Armature current is basically a combination of ID plus IQ, right? This we have derived. Armature current is a combination of ID plus IQ, right? This is all in vector format. These are all ID and IQ are all in vector format. So I can actually replace this equation, right? I can replace this equation. So power will be maximum when delta is 45. So I should actually write here minus. If I don't write minus, that means it will be wrong, right? Because power always flows from higher angle to lower angle. So delta, if I have assumed to be positive, then I have to write here minus. So please don't get confused by this. Power always will flow from higher angle to lower angle. Okay. So now what I know, this is the formula for power, right? And it is telling me it is supplying maximum power. So of course the maximum power value will be this. So P max value will be what? What will be the value of P max? So P max value will be equals to my Vt square. Remember this Vt is a star connection, so this is line voltage, right? So I have to write here phase voltage 400 divided by root 3. Remember this is per phase power, right? Per phase power 400 divided by root 3 whole square divided by 2 into 1 by xq. Xq is given to me. Xq is 4, right? Xq is 4 minus 1 by 6 xd. This will be my maximum power. So three phase power will be what? Three phase power will be 3 multiplied by this. So it will be 400 whole square divided by 3. 3 will get cancelled. 1 by 4 minus 1 by 6. So 1 divided by 4 minus 1 divided by 6. So it will be 0.883 into 400 whole square. So 1333.33. Okay, this will be the uh, reactive power, if I am not mistaken. 400 whole square, yes, 400 whole square into by t. Also there is 8 divided by 2, right? I forgot, there is a divided by 2. So this will be 6 basically 6.67 kilowatt. Okay, this will be the overall active power. Now interesting fact to note here is that I need to find out the uh, I need to find out my this formula. The formula is, what is power equals to root 3 into VL into IA into cos theta, right? So I don't know what is cos theta, power factor. I don't know what is IA, right? These two things I don't know. So how will I be able to find it out? So to find it out, again we have to draw this phasor diagram. So if you remember, if I draw the phasor diagram, that my VT will be here and my EA will lag VT by 45. Okay, this will be my EF. My IA will be somewhere here. Let's assume that IA is anywhere, right? IA is lagging current anywhere here. Okay, so this angle will be 45 and this angle is psi. I don't know what is this angle, and this whole angle will be theta. So I have to find out this psi actually. So this IA current will have two components, right? If you remember correctly, this IA current we used to, one will be along EF. What is the along EF component? It is IQ. So IQ will be equals to IA sin xi, sorry, IA cos xi, and the direct axis component was here. ID was equals to IA sin xi, right? So these two are the components of IA and IQ. Now how will I find out the values? That is what I am trying to think. How will I find out IQ and IA in terms of my VT, right? That is what I am trying to find out. So one more thing I can say this, right? So this is the equation. This is the equation VT. So this VT will have two components. Okay, this VT also will have two components. One will be along EF, other one will be perpendicular to EF. So along EF component will be what? VT cos 45, and perpendicular to EF component will be what? VT sin 45. Now previously I had not explained you this. So if I rewrite this equation, right? If I rewrite this equation, what is my VT actually? So my VT angle 0 is equals to EF angle minus delta plus J ID into XT plus J IK into XQ. Okay, so yeah, now remember this drop is what? Like this VT will have two components. One will be along EF, another one, as I mentioned, perpendicular. So the, if you see this J ID into XD, so ID is perpendicular to this. J ID into XD plus J ID into XD will be here, right? So this will be the component of J ID into XD. JID into XD, and what will be JIQ into XQ? JIQ into XQ will be here. So if I see this component will be IQ is here, right? So plus J into IQ into XQ will be here. IQ into XQ. This I had not previously derived to you, right? So if I notice one thing, that like I will notice two things, right? So my EF, like basically if I equate the components along EF, my VT cos 45 will be equals to EF plus this extra component, right? This drop also will be added here to get VT cos 45, right? So ID plus ID into XD, correct? And my VT sin 45, if I see, only one component is there that is perpendicular to EF, that is this one, right? This drop. So this drop will be equals to IQ into XQ. So will be equals to IQ into XQ. So from here I will be able to find out my IQ and ID current, right? Still I don't know what is EF potential I don't know, but if I'm able to find out IQ, so from here what is my IQ? IQ will be 400 divided by root 3 into 1 by root 2 into 1 by XQ. XQ is 4, right? Sorry, XQ is 4 to 1 by 4. So from here I will be able to find out my IQ current, right? Now how will I be able to find out my IF current, that is the ID current, that is the important portion. How will I be able to find out my ID current, because I still don't know what is my EF. Okay, very interesting fact here, right? Okay, the interesting fact is they have already told that we are operating in zero field excitation. We are operating in zero field excitation. So my EF is 0. So things become even simpler. My EF is actually 0. So EF is 0. So if EF is 0, like I am drawing it a general phasor diagram, but if EF is 0, then things become even simpler. I can easily find out what is my ID. Like EF will have some angle. Okay. Now you might have a doubt, sir, how EF has an angle if it is 0? So there is a concept, zero vector. There is a concept behind zero vector, right? Zero magnitude is 0, but it can have any direction, right? It can have any direction. Magnitude of that vector is 0, but it can have any direction. Okay, so don't get confused that sir EF is 0, how is it there? Okay, so from here I can easily find out what is my ID current. ID current will be VT cos 45. So again same thing, 400 divided by root 3 into 1 by root 2 into 1 by XD. 1 by XD is 1 by 6. So from here I will be able to find out my ID and IQ current, and from here I will be able to find out my IA current, right? So this will be 400 divided by root 3 divided by root 2, just hold on, 400 divided by root 3 divided by root 2 divided by 6, so 27.21 6 amperes. Okay, and this will be 400 divided by root 3 into divided by root 2 divided by 4, so 40.82 amperes. So what will be my IA current? So IA current will be what? It is just a, like magnitude of IA current will be addition of ID plus IQ, right? So it will be ID plus JIQ, something like that, right? Because sorry, not ID plus JIQ. Hold on, what will be my, so what will be my, I have to find out my what will be my IA current. So IA current will be, like it is just, like IA current is a combination of IQ and IQ and ID, right? So how will I find out, my EF is 0, ID IQ is there. I want to find out my IA. What will be IA? How will I find out my IA magnitude? So one thing I know, that basically what is my IA and IQ. So this I have already written over here, right? So what is my IA and IQ? So I know my IQ is IA cos square xi, ID is IA sin, sorry, IQ is IA cos xi, ID is IA sin xi. So if I square these two terms, ID square plus IA square, so IQ square, this will be IA, ID is sin square xi plus IA cos square xi, IA square cos square xi. So from here I can easily find out my IA will be equals to what? IA square will be equals to simply ID square plus IQ square, because sin square xi plus cos square xi will be 1. Okay. So from here my IA will be the square of under root, right? IQ and ID. So it will be this value 27.216 whole square plus 40.82 whole square. Okay. So my IA will be equals to, I will just calculate this value, plus 27.216 whole square whole under root, so 49.06. Okay, this will be your IA value. So I got my IA value. This will be the second answer basically. Okay, what else they have asked? They have asked the electromagnetic torque developed. What will be the electromagnetic torque developed? So what is my three phase power? So this is my single phase power, right? Three phase power will be 6.67 kilowatt. So what will be the electromagnetic torque developed? So electromagnetic torque developed will be P three phase divided by omega s, right? So P three phase is 6.67 kilowatt, right? Divided by the omega s. What is omega s? So Ns is 120 F by P, right? How do I write omega s? So omega will be what? I know omega is 2 pi n by 60, right? So here if I replace this, right, 2 pi into 120 F by 60 is 2 into 2 into pi into F, that's it. So it will be 4 pi F. Am I correct here? So or omega S should be 2 pi F actually. I'm doing some mistake here. Huh? Omega F should be 2 pi F. Okay, but still this is a mechanical quantity, right? This is a mechanical quantity. It's 2 pi n by 60. If I multiply this, 60, 62 will get cancelled. So 2 into 2, 4 pi. Yeah, it is correct only. It is correct only. But okay. Oh, by P is also there, right? Sorry, by P is also there. So one mistake I have made, number of poles is not given. So number of poles should be there. Okay. So it should be two pole machine. Okay, right here. Poles is 2. Okay, this is my mistake. P should be 2. So if P is 2, right, then I can simply write here 2 pi, sorry, 4 pi F, 4 into pi into F, that is 50 hertz, divided by 2. This is my omega s. So I will be able to get the value of the torque developed basically. So torque developed will be 6.67 into 10 cube divided by 2 into pi into F. Okay. So 21.23 Newton meter. Okay, this will be the torque developed basically. Now torque developed is 21.23 Newton developed. That is the answer. And what is the real power absorbed by the motor? Real power absorbed by the motor already you have calculated, right? Real power absorbed by the motor is already calculated. It will be power absorbed will be same, right? 6.67 kilowatt. There is no armature resistance. So whatever power I am delivering from the bus, same power will be absorbed. So this will be the answer. Okay. So you can find out cos theta as well, no problem. You can find out the power factor. So I could have also asked the power factor. Here I could have asked the operating power factor. So operating power factor cos theta will be what? Cos theta, this will be the next answer. Cos theta will be power 6.67 kilowatt divided by VL into IL, root 3 into VL, that is 400 into current is 49.49 amperes, I guess, 49.06. So power factor is 0.196, very poor power factor, because of course excitation is 0, okay, and lagging. How can you say whether it is lagging and or leading? You have to derive the reactive power, okay. So I'm not writing the reactive power value, so that will be a next task. So you can find out the whether it is lagging or leading by seeing the sign of the reactive power, okay. So from here we can find out the power. So now we will discuss about hunting and the ways to eliminate hunting. So let's now discuss about hunting, right? So previously we discussed what is hunting. Hunting in a synchronous machine happens when it is subjected to transient disturbances. The rotor will oscillate around its synchronous speed, right? It will just increase. In NR will be greater than NS, then NR will be less than NS, right? Oscillations will happen. So the causes of hunting are due to mechanical loads, changes in the excitation, basically whichever changes this PE minus PN expression, right, that will be responsible. So either I change the load, either I change PE. So changing PE means excitation changing, either the terminal voltage changes or the synchronous reactance, it will not obviously change, or the power angle delta changes, right. So all those things are responsible for hunting, okay. Changes in the line voltage, if the frequency also changes, right, that also can change this PE, okay. Or there is variation in the load, if there is variation in the load, that means PM will change, okay. So yeah, these are the causes, basically effects. There will be voltage and frequency fluctuations. Hunting can cause undesirable frequency and voltage fluctuations. So if you remember, right, this was the rotor angle fluctuations without damping, okay, and this was the rotor speed. Now all this will cause a current to flow, right. That current, if you remember, the frequency was like it was oscillating, the amplitude was oscillating, right. So that is not desirable because the frequency component of the current has now changed. That is not desirable, right. Increased losses, it leads to increased copper loss because of the varying current, higher I square R loss, okay. Loss of synchronism, so synchronism can be lost, right. If I'm near about, basically if I'm near about the unstable region, right, this is my delta, this is my PE, okay. So if I'm near about here, near the unstable region, unstable region, okay, then of course even if there is slight disturbance, it will not oscillate anymore, it will go back directly. If I'm here, then it is fine, it can oscillate, but this can cause loss of synchronism can be lost, right. So these are all the problems. So what we do, we provide damping mechanism to reduce the oscillations because this is undamped. So what I will do, I cannot totally remove the oscillations because hunting is inherent in synchronous machines. But what I can do is I can reduce it by providing some damping. Damping, what will damping do? So if I start from here, right, slowly the oscillations will die out. So we provide few damping mechanism known as damper windings. So damper windings are windings which will be connected on the rotor poles, okay. So they will be connected on the rotor poles. These windings develop a damping torque that will oppose the rotor oscillations, effectively damping the hunting effect and helping the machine to stabilize quickly. So we will see it, basically we will see uh, what is damper winding. So already we have discussed that what happens in hunting, right. So initially, let's say I am at this steady state position delta naught, suddenly I increase the load. If I suddenly increase the load, so what is happening over here, my PM is greater than PE. So if my PM is greater than PE, that means what is the equation, the most basic equation is what, the torque, right. Torque is proportional to PE minus PM, right. So if PM is higher, I am developing a negative torque. negative torque basically means my d omega by dt will be negative. If it is negative, that means my omega r will simply reduce. If omega r is reducing, that means my delta angle, rotor angle will increase, right? Because speed is reducing, so delta will increase. Okay, here speed is reducing, so this is moving slowly, this is moving much faster, so this relative angle will increase. If delta increases, I will go along this path, right? At this point, the developed torque will be zero, equivalent torque will be zero. But what will happen at this point is that the rotor speed is still lower than stator speed, so it has not reached steady state. So still the delta angle will increase because rotor speed is not equals to stator speed. Rotor speed is lower than the stator rotating magnetic field. So delta will still increase, keep on increasing, and I will reach certain point here C, and then again in this region my rotor will accelerate. Why? Because the developed power is greater than the mechanical power. So NR will increase. Again, I will reach this point where NR will be equals to NS. But again, this point is not stability point because torque is still positive. So now NR is higher than NS. So it will try to reduce. Okay. NR will try to reduce. Why? Because the relative angle will reduce. If NR is higher, this is rotating much faster than NS. So this relative angle between NR and NS will reduce. Okay. And this is what happens in hunting, right? So that is what we want to damp out. So these are the cases that we have discussed over here. So I don't want to go through this because in the previous lecture I have explained each and everything. Okay. So these are the effects of hunting. What can be problem? So we will dampen out these oscillations with the help of damper windings. Okay. So damper windings, I will show you what are damper windings basically. Here we have damper windings. Okay, these are my damper windings. So damper windings will be placed on the rotor poles. Okay, these. So this is my field winding that will be placed just on the side of the poles, and this will be my damper winding. So damper winding are nothing but short rotor bars short circuited and hole punched, right? So what we do is, these are aluminum or steel bars. What we do is we punch them in the head and we short circuit them. So what happens when there is oscillation? Whenever there is oscillation, that is NR is not equals to NS. Whenever NR is not equals to NS, what will happen? There will be a bit of relative speed, and if there is bit of relative speed, it is just like induction motor. So in induction motor, what happens? If there is relative speed between the stator flux and the rotor flux, what will happen? The flux will cut the rotor bars. If the flux cuts the rotor bars, that means there will be an induced EMF, and that induced EMF will oppose the cause. What is the cause? Cause is basically speed of the rotor and the stator field is not same. That's why there is flux cut, right? So that induced EMF will induced and torque such that a current will be induced, and that current will induce a torque such that it oppose the oscillations. So that is what our damper windings will do. That's it. That's the summary. That's the bottom line. Nothing else you need to understand. That is it. Okay. So our damper winding will do what? Damper winding is also known as, this term I also don't know. Amateur windings, I also don't know how to pronounce it. Okay. These are specialized windings integrated in the pole faces, rotor pole faces of synchronous machine. They are very important for enhancing the machine stability. Remember, damper windings will be used only in salient pole machines. damper winding will be used in salient pole machines. Okay, they will not be using cylindrical machines because already for the cylindrical it is symmetrical. Cylindrical poles are symmetrical, so they automatically it induces some EMF on the pole faces. So we don't need an additional damper winding. Automatically it will basically oppose the oscillations. Okay, so construction of damper windings, these are placed, these are positioned within slots precisely cut into the pole faces. They are typically fabricated from copper, brass or aluminum bars. They are short circuited so that currents can easily flow. Okay, and that current will develop a opposing torque. Okay, this is again repeated actually. So in cylindrical rotor, the property of damping is inherently present. Why? Because it is already very uniform. Okay, so automatically there will be few short circuit current that will be flowing through the rotor so that it opposes the oscillations. This only will be used in salient pole rotors. Okay, so this is the key point that you have to understand. So now, so there are dual purpose of damper windings actually. What are those dual purpose? First purpose is to remove the oscillations. Okay, the oscillations, hunting oscillation mechanism, right? This we already know. This I have already discussed how it will remove the oscillations. Okay. Second one is actually to starting. It has, yeah, damper winding, how damper winding working, all these things I have already explained, so I am not reading it. It is written, whatever I have explained is written over here. Now second one is to enable the self starting. As I have mentioned, the average torque is 0 initially when the rotor is at rest, right? So the synchronous motor inherently lacks self starting capability when directly connected to a three phase AC supply. Okay, to a three phase AC supply, it will lack the self circuit capability. This is because the stator rotating magnetic field establishes itself almost instantaneously. Basically, if the rotor is here, right, and like as the stator speed is very fast, right, so stator field will move with ns very fast. So for certain period it will be here, then again it will ns will be here. Basically the north pole will be here, and after a split second, right, it will again reach here, again it will reach here. So basically the north pole is traveling so fast, the north pole of the rotor is not able to align with the stator properly, right? So average torque during starting when the rotor is at rest will be 0 because north pole is moving so fast, it is not able to match with the south pole. Because let's say at t equals to 0.001 second, the north pole is here, then again at t equals to 0.002 seconds, the north pole is here. So here what kind of torque I'm getting? Repulsion torque, right? Here I'm getting attraction torque. Okay, here I'm getting repulsion torque. Okay, so that is the problem. So for half time period it is getting attraction torque, for a half time period it is getting repulsion torque. So net torque is 0. That's why there is no inherent starting property of synchronous machines. Okay, so to resolve that, we have damper windings. I have told you, right, damper windings basically tries to reduce the relative speed between the stator and rotor. Whenever there is relative speed between the stator and rotor, it will try to oppose it. It will try to make both of them same speed. So again, damper windings, what will happen? If the stator poles are rotating, a effect like what? Induction motor. Remember, right? It is same as induction motor. So the stator poles are rotating very fast, and I have damper windings here. Due to that, there is relative speed difference. Due to that, an EMF is getting induced, and due to that, a current will flow, and that current will produce a torque such that it reduces the relative speed between the stator magnetic field and the rotor. So damper winding is useful in this case as well for starting. So damper winding has two use cases. One is used for starting, another one is used for reducing the oscillations. So we have already discussed that in cylindrical rotor machines, due to solid steel rotor body, it will possess some natural damping characteristics. So natural damping will be there because the body of the cylindrical rotor is symmetrical and solid steel. But still we will need the damper windings for starting, right? So starting we will need. So anyways, so damper windings will be present in both cylindrical and the salient pole rotors. So now let's understand one more thing. Okay, let's now understand one more thing, that is regarding the resistance. So in case of a motor, the damper winding, right, damper winding is required for both starting and for damping the oscillations, damping out the oscillations. Okay, and one more thing I can say, for generator, do I need it for starting? For generator, the damper winding is only required for damping the oscillations. And one more thing, if you remember, what was your torque proportional to? Induction torque. It was proportional to the rotor resistance, right? If you remember, rotor resistance. So as I need the damper windings for starting, here I need higher starting torque. So the resistance for damper winding of a motor has to be higher than resistance of damper winding for the generator, because in case of generator I just need it for damping oscillations, right? So for damping out oscillations, that I don't need that much higher amount of torque because the relative speed is somewhat lower, but starting relative speed is very high, so it will induce high voltage. If it induces high voltage, it has to support that amount of current, right? So start, like, I have to produce higher starting torque. So that is possible if I give more damping resistance. Okay, I hope that is clear. One more point I want to mention here is that damper winding will only come into action if it is, if the speed is nr is not equals to ns, right? If the speed is nr is not equals to ns, then only damper windings will come into action. So during normal operation, so this is during either starting or oscillations. Okay, so there will actually be no copper loss, remember it. So during normal operation, so normal operation means nr equals to ns. Normal operation, there will not be any induced EMF because there is no relative speed between the rotor and the stator. Hence, damper winding will not come into action. Okay, so that is what I have written over here, that for motor, right, the desired, like, damper winding resistance will be higher. For generator, the damper winding resistance will be lower. Okay, that is what is written over here. Okay, generally the desired resistance for damping oscillations or hunting is lower only, but as in case of motor I need it to start as well, I need higher starting torque. So generally, like, this is a practical case scenario that the damper winding resistance of motor will be higher than that of generator. So in turbo alternators, there is no separate damper bars required for oscillations, okay, for damping effect. But for starting I will still require some starting mechanism. Okay, for reducing hunting, damper bars are not required for cylindrical rotors, but for starting I will still require it. Okay, so let's do few questions. Few theoretical questions have come in GATE examination. So this is the first question. In synchronous machine, hunting is predominantly damped by mechanical losses in the rotor, iron losses in the rotor, copper losses in the rotor, copper losses in the stator. So basically, the hunting is generally damped by the induced EMF on the rotor side, due to which some induced current that flows, and that produces a reverse torque. So this is known as the current. So what is it? What will be the loss? I rotor into the rotor's current, right? Rotor resistance, R square. So this is the loss, this is the amount of power that is getting developed to oppose the hunting. So copper loss in the rotor will be correct answer, because it is a rotor current that is able to develop the opposing torque of hunting. Let's now solve the next question. So in hunting, mostly theoretical questions will come. When rotor speed of a synchronous machine exceeds the synchronous speed. So rotor speed is higher than synchronous speed. When does it happen? It happens, if you remember, in case of induction motor, it was the case of induction generator. In induction generator, the rotor speed is higher than stator speed. The slip is negative. Okay. So what they are telling me, during hunting, the damper windings will produce what kind of torque? Torque similar to synchronous motor? No, because it is not similar to synchronous motor. Synchronous motor, whatever torque it develops for the rotor speed to be equals to ns. Torque similar to DC motor? No, it is not a DC machine, it is AC machine. Torque similar to induction motor? Is it? Is it the same torque similar to induction motor? So the torque produced in induction motor is the kind of torque that happens when my NR is less than NS, right? NR is less than NS, my NR rotor follows the stator. That is a torque developed in induction motor. In induction generator, my NR is greater than NS. So this is torque. This kind of torque is known as torque similar to an induction generator. When my rotor speed is higher than stator speed, it behaves as a induction generator. Okay, that's why the torque will produce also will be like a induction generator. So option D will be the correct answer of this question. So these are few theoretical questions that generally have been asked in hunting. So in the next lecture, we will discuss about the starting of synchronous motor. How can we start? Basically, already we have discussed using damper winding. So that we will discuss, and also we will discuss about voltage regulation and few other tests. Thank you, and I will see you in the next lecture. Until then, happy learning.